Hello, in this lecture we are going to study the modeling capabilities of neural networks, investigating which class of functions can be learned by neural networks. In this context, we will illustrate that the nonlinearities introduced by the activation functions are key components of neural networks. This gives neural networks high enough representation power to learn most of the functions we can find in real-world application. In this lecture, we will focus on neural networks with one hidden layer of dimension k and a single output unit. However, under some conditions, all the results can be generalized to multiple hidden layers and multiple output. The question we want to answer is the following. What kind of functions this class of neural networks can learn? Note that without activation function, f of x would be a linear function, and in that setting, the neural network will be able to learn only linear functions, no matter how many numbers of layers and neurons you have. However, with the nonlinearities introduced by activation functions, we can hope to also learn nonlinear functions. Nevertheless, a neural network is still a continuous function. Consequently, we can only aim to learn continuous functions. But there are continuous functions that are nonlinear and highly erratic. So the question is, can neural networks learn all continuous functions? A positive answer to this question has been given in the 80s by Sebenko. In his seminal paper, he has shown that for any continuous function g defined on a compact set and any error threshold epsilon bigger than 0, there exists a single hidden layer neural network with a large enough hidden layer that is closer than epsilon to g. That is, for any input point, the distance between g and the neural network is smaller than epsilon. Consequently, we can say that infinitely wide neural networks are universal approximators. A wide enough neural network, where wide is defined as the number of hidden neurons, can approximate any continuous functions arbitrarily well. The proof of this theorem is not going to be discussed in these lectures, but I leave to you a reference to the original paper in case you are interested. It is important now to stress some implication of the theorem. The theorem is stated for sigmoid activation functions, but it extends to the ReLU and hyperbolic tangent as well as multiple output units. This theorem shows us that neural networks are universal approximator in the limit of infinitely wide hidden layers. For a finite number of hidden neurons, the error cannot be assumed to be 0. Consider, for instance, neural networks with ReLU activation functions. With finitely many hidden units, the neural networks will necessarily be a piecewise linear functions with finitely many pieces, and so it can only learn exactly that class of functions. An important aspect to have in mind is that this theorem does not tell us anything about how to learn the desired function. It just guarantees that there exists a neural network that can learn it up arbitrarily well. As we will see, learning with neural network is a non-convex optimization problem, for which the optimal solution in general cannot be found. Another important aspect to highlight is that similar results can be obtained for neural networks with a fixed number of hidden neurons per layer, but infinitely many layers. Now, if you think back at the universal approximation theorem, a natural question is, but if neural networks with one hidden layers are universal approximator, why do I need to go deeper? This is a good question, and there has been research in this topic. In particular, for many problems it can be shown that by going deeper, we require less parameters to approximate a given function, facilitating the learning process. Intuitively, by using deep architecture, we are implicitly biasing our model towards functions that involve composition of several simple functions. This facilitates the learning of complex functions that are composition of many other functions. An example can be shown in the following figure, taken from a paper from Rolnik and Tagmark. In particular, the figure plots the performances of various neural networks architectures in predicting a polynomial function, ranging from red, high error, to blue, low error. It is possible to observe that at least one hidden layer is required to learn the function with low error. We need nonlinearities. In general, at least up to a given number of hidden layers, more hidden layers means less neurons per layer and in total to achieve a given error. While this is an empirical study, if you work with neural networks, you will see that for complex tasks, multiple hidden layers will often be required.